We defined yesterday centripetal force, force in quotation marks, is the force that pushes an object toward the outside of the circle. We also said yesterday that centrifugal force doesn't actually exist. Centrifugal with an F doesn't actually exist. How do we feel ourselves being pushed to the outside of a circle when it doesn't really exist? Well, the same way as we feel ourselves being pushed into the back of our seats when we accelerate from rest at a stoplight. When we're sitting there at a stoplight, we put our foot on the gas pedal, we feel as if we're being pushed into our seats, but we're not. What is it really happening? Well, really our inertia wants to keep us at rest, and as the force of the seat pushes us forward, the forward force of the seat combined with our inertia makes me feel like I'm being pushed backward. So forward force and inertia makes me feel a force backward that doesn't actually exist. Now, when I'm going in a circle, what happens? Well, there's a centripetal force pointing toward the center of the circle. That's a real force. It's caused by friction. It's caused by tension. It's caused by some wall pushing you in. Whatever it's caused by, the centripetal force is a real force. The inward force combined with your inertia that wants to take you in a straight line makes you feel as if you're being pushed outward. So forward force combined with your inertia makes you feel like you're being pushed back into your seat. Inward force combined with your inertia makes you feel as if you're being pushed outward. That centrifugal force with an F is that fake force that makes you feel as if you're being pushed outward, but is really just what? If we had to describe this in one word, what would that word be? Starts with an I. What is it? Somebody said it? Inertia. It's really just inertia. Whenever we have an object experiencing a force or accelerating, there is always a pseudo force or a fake force that pushes in the opposite direction. So a real force forward combined with my inertia, I feel like I'm being pushed backward. A real force toward the center of the circle combined with my inertia, I feel like I'm being pushed to the outside of the circle. That centrifugal force, that force that pushes you back into your seat, those are both pseudo forces or fake forces that are always opposite to the real force. Every time, name a situation where you accelerate. Every time you accelerate, you will feel a pseudo force or a fake force, a force that doesn't really exist, in the opposite direction. It doesn't mean that there really is that force, it just means that we perceive it. Let's move on now. Let's talk now about something new, specifically vertical circles. When we have analyzed problems thus far, it's been an object going around a circle on a horizontal plane. Now we want to talk about objects going around circles in vertical planes. Like a roller coaster, right? When a roller coaster car goes around a vertical circle in a roller coaster, you can imagine that's what most people are afraid of on a big roller coaster, right? Is that upside down circle. In my experience, that's actually not the worst part of a big roller coaster, the upside down circle, because you don't even often know that you're upside down unless you look sideways and see the world upside down. When you're going forward, you perceive it as if you're just going up a hill the whole way through this vertical loop. But that's what tends to scare people the most, people that have never ridden one the most. We want to analyze those vertical circles right now, whether we're talking about a roller coaster or whether we're talking about something as simple as me swinging my keys like this. Clearly, if I take these keys and stop them right at the top there, they're going to fall, right? And if I spin them fast enough, they're going to go in a vertical circle like this and not fall out. There's going to be a speed at which it makes it all the way around, below which the keys are going to fall out of the circle. We're going to learn today and tomorrow how to find what that minimum speed is. We're also going to learn to analyze the forces involved at various points around that circle. In a vertical loop, we're going to analyze two spots, two situations. One where the object, whether it's a roller coaster cart or whether it's the bucket of water that we just used in our demonstration, is at the top of the loop, and when it's at the bottom of the loop. We could analyze when the bucket of water or the roller coaster is at the side or some kind of diagonal like this. It wouldn't be that much harder, but the reality is we don't need to. The extremes of forces occur at the top and the bottom. And if I'm engineering a roller coaster, I want to engineer it according to the extremes, not according to the things in between. So I don't need to analyze really the sides or diagonals like this. I need to analyze the top and the bottom. So that's what we're going to learn to do today. In this situation here, whether it's a bucket of water, whether it's a roller coaster or a cart, there are two forces acting on the object in both positions, the top and the bottom. What's one force that acts on both of these? Somebody said gravity. Which way does gravity act? Down. In both cases, right? Gravity's going to act down right here, and gravity's going to act down right here. Do you agree with that? Yeah. This isn't rocket science, right? Not yet. Gravity is acting down on the bucket of water, on the roller coaster cart, whatever it is that's going in a circle, the keys, if I swing them around in a circle, no matter where the object is in the circle. Now, don't worry about direction of force right now, but what other force acts? The normal force, right. Whether that normal force is the force of the track, or whether that normal force is provided by the bottom of the bucket that has the water in it, or whether that normal force is provided by the string that holds the keys. The other force is the normal force. Now, let's look at the situation at the bottom of the circle here. Which way does the normal force act? Which way does the normal force act at the bottom of the circle here? It acts up. Notice that I have the normal force at the bottom of the circle drawn bigger than gravity. If the normal force acting up isn't bigger than gravity, then this thing isn't going in a circle. Does that make sense? You have to have a net force toward the center of the circle, otherwise it doesn't go in a circle. When you're going around a vertical loop on a roller coaster, the normal force will always point toward the center. Now, when I get to the bottom, what happens? Well, the normal force now isn't bigger than gravity necessarily, and that's why I don't go in a circle anymore. That's why I come out of the circle, because the normal force pointing toward the center isn't bigger than gravity. What other force do I have acting up here? Normal force as well. Which way does it act? Which way does the track act at this point? Downwards, yes. Now, we don't know how big that normal force is. It could be smaller than gravity. It could be bigger than gravity. It all depends upon how fast we're moving at this point. We know it's downward. We know it helps gravity, but we don't know how big it is until we do some calculations with the numbers that we would be given. Now, some of you might be thinking right now, this looks an awful lot like some stuff we did in our last unit. Remember our elevator problems? Remember our inclined plane problems, our pulley problems? We had free body diagrams drawn in each of those. What did we do after a free body diagram was drawn? What was step 2? This is step 1, right? Draw a free body diagram. What was step 2? Yeah, get all the forces together. What was that? Yeah, F net is equal to the sum of the forces. In this case, it would be Fg plus Fn, the force of gravity plus the normal force. You remember what step 3 was? No, not yet. Well, we get F net is equal to what? No, it's not gravity times something. What is it? Yeah, mass times acceleration, m times a. And it's still m times a. Hold on before you write this step down, okay? It's still m times a. But if we're going in a circle, that acceleration is a very specific type of acceleration that we call the centripetal acceleration. So instead of saying m times a, we'll say mv squared over r. It's the same thing, right? But a is a specific type of acceleration called centripetal. And then step 4 would just be, just like it was in our last unit with these problems, sub-inner numbers. Sub-inner numbers and solve. Well, this would look exactly the same. This bottom one would look exactly the same, right? Step 1, draw a free body diagram. Step 2, F net is equal to the sum of the forces. Step 3, mv squared over r is equal to the sum of the forces, Fg plus Fn. Step 4, sub any numbers and solve, right? Same thing. What I want to do right now, though, is look at the signs of these forces. Notice whenever I'm just doing the F net thing, everything's positive. The equation shows positive. But when I sub in numbers, I have to worry about positive or negative. Which way is gravity acting at the top of the circle? Down. Sure, it should be negative, right? Which way is gravity acting when we're at the bottom of the circle? So it should be negative as well. What about the normal force when you're at the bottom of the circle? It's positive because it's acting up, right? Now, we don't worry about negative or positive until we sub numbers in, right? But once we do that, we have to put the signs in as well. What about the normal force when you're at the top of the circle? It's downward, so it's going to be negative, right? What about the centripetal force at the top of the circle? The centripetal force, which is the net force. Which way does the net force, the centripetal force, act when you're at the top of the circle? When you're at the top of the circle, where is the center of the circle? Below you. So which way does the force toward the center of the circle act? Down, right? Downward. So we're going to say that centripetal force when you're at the top of the circle is downward, negative. What about at the bottom of the circle? This one's a bit trickier. When you're at the bottom of the circle, as long as you're going in a circle, where's the center of the circle? Up. So the centripetal force must be toward the center or upward. We're going to get a positive value. Again, I don't want you to worry about signs of forces at all until you sub numbers in. Then you got to really pay attention to whether they should be positive or negative. Look, it looks almost exactly the same other than signs. Get the signs right, get the equations right. These aren't very hard. These are no harder than what you did in last unit. In fact, they're easier than some of the questions you did in our last unit. Let's do an example here. Example number 3 in your notes package. This is a 1,050-kilogram roller coaster car, including a passenger, is moving on a vertical loop of radius 10 meters at a speed of 35. By the way, this is a crazy high speed for this roller coaster. 35 meters per second. That's like, I don't know, 120-ish kilometers per hour on a roller coaster that has a radius of 10 meters. This is really, really, really fast. What's the force of the track pushing up on the roller coaster when the car is at the bottom of the loop? Let's draw a free body diagram. Don't ever skip this step, okay? Draw your free body diagram every time. Here's the bottom of the loop. Gravity is acting down. Normal force is acting up. F net is equal to the sum of the forces, Fn plus Fg. F net is mv squared over r, Fn plus Fg. Notice I haven't paid any attention to negatives yet. Just like in our last unit, we didn't worry about negatives until we subbed in numbers. Well, now it's time to sub in numbers. M is 1,050 times V, which is 35, over R, which is 10 meters, equals Fn plus 1,050 times 9.81. I'm not going to worry about the sign for the normal force because I didn't sub a number in for that. But I do need to worry about gravity. Is gravity up or down? Down. So it's going to be positive or negative? Negative. What about the centripetal force? Which way does it act? You're at the bottom of the circle. Where's the center of the circle, Luke? Yeah, so the centripetal force will be positive. Let's calculate this now. On the left-hand side, we have 1,050 times 35 squared divided by 10 gives us a value of 128,625. And then 1,050 times 9.81 gives us a value of 10,300.5. We take the 10,300.5 over by adding. And we get to 2 digits. We're going to say Fn is equal to 1.4 times 10 to the 5 newtons. That's the normal force. Wait a sec. What am I looking for? force of the track. They're not the same thing. Normal force, the force of the track. Yeah, I just solved for the force of the track. 1.4 times 10 to the 5 newtons. You can imagine if you're an engineer designing a roller coaster, it might be useful to determine what the force is at the bottom of the track so that you can design the track to be strong enough to hold that force. It's great to design this beautiful roller coaster, but if the bottom of the track can only hold 1.1 times 10 to the 5 newtons, and you have 1.4 times 10 to the 5 newtons, then the track will break. And that doesn't usually end well for the people on the roller coaster. Let's look at B, then we'll take a little break. What's the force of the track pushing, shouldn't say up, pushing on the roller coaster when the car is at the top of the loop? Gravity is acting down. The normal force is acting down. Do you expect the normal force, the force of the track, to be greater or less than what we just found? Yeah, it is going to be less. Because gravity and the normal force are helping each other here, right, at the top. At the bottom, they're going against each other. Normal force doesn't have to be as big at the top. So we're going to say F net is equal to the sum of those forces, Fg plus Fn. F net, actually, let's say Fn plus Fg, just to be consistent with the last one. Doesn't matter. F net is mv squared over r. Sub some numbers in here now. mv squared over r ends up being 128,625. I kind of skipped a step there because I already had that number, right? Is that okay for me to skip that step? Yeah, I already calculated it, right? I don't have to show it again. Equals Fn plus 10300.5. But gravity should be negative, right? When you're at the top of the circle, gravity should be negative. What about the centripetal force right here? It's negative as well because you're at the top of the circle and it's downward from you. Now, when we say negative 12,000, plus positive 10,000, it should give me a value of negative 1.2 times 10 to the 5 newtons. You guys tell me the normal force should be greater or less than it is at the bottom? Yeah, you guys said it should be less, right? Because the forces are helping each other. Is it less? Yeah, a little bit. A little bit. When you're going around that loop on our field trip day, you're not going to notice a huge difference between the top of the loop and the bottom of the loop. You're not going to be able to really tell when you're upside down and when you're not upside down, but there will be a difference, a small difference between the top and the bottom. Let's do question C now. Hey, we just went from two, not crazy hard questions, but kind of hard, to question C, which is actually a pretty straightforward question. What's the actual weight of a 50-kilogram passenger on the roller coaster? Nothing rocket science to this at all. It's just the force of gravity, m times g. So we're going to say it's 50 kilograms times 9.81, which is 490.5 newtons. Now, we're going to round that to 2 digits, 4.9 times 10 to the 2. And I suppose technically it probably should be a negative value because gravity is acting down, but we're not going to lose any sleep over that. 4.9 times 10 to the 2 or negative 4.9 times 10 to the 2. I mean, we could have done this on day 1 of our last unit, right? We didn't need circular motion analysis to do that. Question D says, what's the apparent weight of a 50-kilogram passenger on the roller coaster when the car is at the bottom of the loop? What am I looking for there? What am I solving for apparent weight? You did this in your last unit. Remember on elevator problems? What's the apparent weight of somebody in an elevator? What did you solve for? The normal force. That's what you're solving for here too. The apparent weight is the normal force. So you're going to do the problem the same way as you did question A, except that you're using a mass of 50 rather than the mass of the car. At the bottom of the loop, we have a force of gravity acting down, and we have a normal force acting up. We say F net is equal to the sum of the forces. We say mv squared over r is equal to the sum of the forces. then we start subbing some numbers in. Mass is 50 kilograms. V is 35 meters per second, this crazy high speed. Over R, which is 10 meters. Fn plus m times g. Mass is 50 again, times 9.81. Now, at this point, since we sub numbers in, we have to worry about signs, right? At the bottom of the roller coaster, Jen, at the bottom of the roller coaster, is gravity up or down? Jenna, you have a low voice all of a sudden. What is it, Jenna? Yeah. Good. It is down, so we're going to make it negative. Was that Luke? Yeah. I can see how it sounds like Luke, though. You know, Jenna, Luke. Okay. Luke. Centripetal force when you're at the bottom, is it up or down? Yeah, so it's going to be positive. Let's calculate these numbers. 50 times 35 squared divided by 10 gives me a value of 6125. Fn subtract 490.5. Now, if we take that 490.5 over to the other side, we get a value of 6615, which, we're going to round that to 2 digits, we get 6.6 times 10 to the 3 newtons. So the actual weight of the person is 4.9 times 10 to the 2. The apparent weight is 6.6 times 10 to the 3. So, man, this person feels pretty heavy compared to how heavy they really are. You're going to get a question on your field trip assignment that asks you to do exactly what we just did, just with different numbers. The follow-up question to that will be, how many G's did the person experience? In other words, how heavy did the person feel compared to the actual weight of the person? Find the number of G's. You're not asked to do this in this question, but I'll just show you how you would do it. You would say the normal force, which is the apparent weight, over the actual weight. The normal force, 6615, divided by the actual weight, 490.5, gives me a value of 13.5 or 13. So in this case, this person would feel 13 times heavier than he or she really is. Don't worry, when we go on our field trip, you're not going to feel 13 times heavier than you are. That would make you pass out almost instantly. And for any sustained period of time, would actually cause a lot more serious damage than losing your peripheral vision. That's a big amount. That's a big amount. Now, what's the apparent weight of a 50 kilogram passenger at the top of the roller coaster? Almost the same thing, right? Let's analyze the top now. Gravity's acting down. Normal force acts down. F net is equal to Fn plus Fg. Same as it was before. mv squared over r is equal to Fn plus Fg. Now, we already calculated mv squared over r, so we don't need to do that again. It was 6125. Fn is, that's the apparent weight, what we're looking for. Fg was 490.5. Nick, is gravity positive or negative at the top of the circle? Yeah, because it's acting down, right? Is the centripetal force positive or negative when we're at the top of the circle? Haley, is it positive or negative, the centripetal force? Negative. Yeah, because it's acting down as well toward the center of the circle. So the only difference between this question and the last question is this, right? Solve this. This goes over by adding to the other side. We end up getting a value of 5634.5. Which is negative 5.6 times 10 to the 3 newtons. So at the top of the circle, you feel a little bit lighter than you did at the bottom of the circle, right? By the way, if you wanted to find the G's here, it would be 5634.5 divided by 490.5. That'll give you a value of 11. Does it make sense? At the top of the loop, you'd feel a little bit lighter than you would at the bottom of the loop?
Yes.
Because gravity and the normal force are helping each other. Whereas at the bottom of the loop, the normal force has to act against gravity. So of course that normal force is going to be bigger there. I'm going to have you work on 2 questions, which is really 4 parts because they both have A and B. Worksheet number 21, questions number 1 to 2, please.